Hi, I'm Ryan, and I'm a student at Jericho Senior High School. And this is my project, creating a predictive algorithm to estimate the impact of functional groups on silicon anode binders. I've worked very hard with my mentor, Maura Appleberry, on this project. Silicon anodes will revolutionize battery technology. Current batteries utilize graphite anodes. However, silicon is much more promising as an anode material because it is over 11 times the theoretical capacity of graphite. Additionally, it's more abundant, it's cheaper, and it's eco-friendly, therefore providing a path for affordable clean energy. However, a major drawback of silicon is that it can expand up to 400%, reducing the capacity significantly and making the batteries useless. Figure 1 represents the change in a silicon anode after like an electric current is applied to it, where figure 1a represents a pristine silicon anode before cycling. Cycling is when you apply a charge and discharge. And then figure 1b represents the same silicon anode after an electric current is applied, and the silicon molecules expand dramatically, and the anode distorts to make it useless. However, a solution exists that prevents the silicon expansion. There are molecules known as binders that prevent the silicon expansion. Figure 2 represents the impact of binders on silicon anodes. The dashed line at the bottom represents the capacity degradation of graphite, which is the current anode material. And you can see it starts very low, but it's able to maintain that capacity throughout. Meanwhile, silicon without a binder starts at a much higher capacity, but it loses that capacity almost instantaneously, and it levels out immediately. Silicon with a poor binder suffers a similar fate, but to a lesser extent. What researchers are aiming to find is silicon with an optimal binder, which is able to start with that high capacity, but maintain that capacity throughout. This is why an effective binder is needed. However, there are millions of binder molecules that exist, so it's difficult to know which ones to test. This is why I decided to compare the molecules based on known and unknown binder mechanics. A known binder mechanic is that the presence of polar functional groups improves binder performance. Polar functional groups, such as hydroxyl and carboxyl groups, are able to form strong hydrogen bonds with the silicon dioxide found on the surface of silicon anodes, as shown in figure 3. But there is not a lot known about binders. And in order to capture these unknown mechanics, it's important to use a strong predictive algorithm such as machine learning. Therefore, I asked, can an optimal binder be identified from millions of candidates by using functional group density in a machine learning algorithm? In this study, I will do 3 things. First, I will build a model that will be able to accurately predict the capacity retention given any set of standing testing conditions and any binder. Second, I will implement my model to identify the optimal amount of hydroxyl and carboxyl groups in a molecule that can be. Finally, I will apply this model by screening an organic molecule database to identify a molecule that actually has these optimal hydroxyl and carboxyl characteristics. I collected my data from 100 different binders in 39 different articles. For each different binder, I was able to look at the capacity degradation graph, and I was able to estimate the capacity values for every cycle between 0 to 100. Just a reminder, a cycle is the amount of time that it takes to charge and discharge a battery. And I was able to identify 100 values for all 100 binders, thus giving me a total sample size of 10,000. The independent variables I used for the study were hydroxyl group density, carboxyl group density, current density, mass loading, silicon ratio, binder ratio, electrolyte additive amount, and cycle number. Most of these variables are not important, but the 2 that are important are hydroxyl group density and carboxyl group density. This is because these are novel independent variables that I created for the purpose of quantifying the amount of hydroxyl or carboxyl groups present within a molecule. This independent variable can be calculated with equation 1 by considering the amount of hydroxyl and carboxyl groups with the amount of non-hydrogen atoms within the molecule. The dependent variable I used was the capacity retention of a battery measured as a percent. I created my model using the TensorFlow library in Python. When initially analyzing the data, I noticed there was an obvious nonlinear trend in the capacity. It's best represented as a power function. This means that the simple linear model cannot accurately predict capacity decay, which means a deep learning model is necessary. A neural network is one such deep learning model that's good at recognizing these nonlinear trends, and it's also easy to use, which is why I chose it to use for my study. I created the neural network in such a way where I could input all 8 independent variables and output a single predicted capacity retention. This predicted capacity retention is very important because it serves as a standard comparison for futures to see the significance of the carboxyl and hydroxyl group densities. My neural network was quite accurate with an R-squared value on the validation set of 0.78. This is significant considering that an R-squared value between 0.7 and 0.9 is considered highly accurate in current neural network literature. Therefore, I was able to conclude that a neural network model can use binder functional group density to predict silicon battery capacity retention with high accuracy. Next, I implemented my model. In order to do this, I wanted to compare the hydroxyl and carboxyl group densities with my dependent variable, predicted capacity retention. And I wanted to do this using a color map. So to create my color map, I standardized all the other independent variables so they would not have any impact on the predicted capacity retention. So I could just isolate the performances of hydroxyl group content and carboxyl group content on the predicted capacity retention. The resulting graph was figure 7. And you can see that the higher carboxyl group density and the higher hydroxyl group density indicates to a higher predicted capacity retention, while vice versa. Particularly, the maximum point occurs when the carboxyl group density is 0.5 and hydroxyl group density is 0.37, while the lowest predicted capacity retention occurs when the carboxyl group density is 0 and hydroxyl group density is 0. This is actually consistent with current battery literature because polyvinyl difluoride is one such binder that's used in silicon anode research, and it has 0 carboxyl group density and a 0 hydroxyl group density. And it's often thought to be the worst performing binder in silicon anode research. And my model is able to predict that PVDF is indeed the worst performing binder. This means that there's a good chance that the carboxyl group density of 0.5 and a hydroxyl group density of 0.37 is likely to be the highest predicted, would likely give the highest predicted capacity retention. Therefore, I concluded that my model can identify the optimal and hydroxyl and carboxyl group density of a binder for any set of experimental conditions. Finally, I was able to implement my model by running my model through the PubChem organic molecule database, which had 7 million molecules. And from there, I was able to identify the top 50 candidates with the highest predicted capacity retention. However, of the top 50 candidates, only 2 are of significant importance, those being EPA and tartaric acid, because of their commercial availability. Figure 8 represents the comparison of the relative predicted capacities of tartaric acid and EPA compared to polyacrylic acid. Polyacrylic acid is a common binder used in silicon anode research as a standard of comparison because it's okay, and you can see that in the conditions that I listed, tartaric acid and EPA have a predicted capacity retention of almost double that of polyacrylic acids. Figure 9 represents the molecular structure of tartaric acid, and you can see it has a lot of carboxyl and hydroxyl groups for its relatively small size. Additionally, tartaric acid is of particular importance because it's already been used in the field of battery research as an electrolyte additive in zinc-ion batteries. The researchers of that paper identified that tartaric acid actually has promising electrochemical capabilities that could make it useful as a binder. Therefore, I concluded that my neural network model can identify optimal and feasible binders from millions of candidates. In conclusion, my study was a novel study because it gave the user the ability to compare millions of binders in an instant, whereas previous studies were only able to compare 2 binders at a time with limited equipment and physically testing the batteries through electrochemical means. And I provided a machine learning algorithm that would weigh the effect of polar functional groups to identify the predicted capacity retention of silicon batteries with different binders. In addition, I was able to identify 2 molecules that had the optimal conditions that could be used as potential binders in the future, those being EPA and tartaric acid. Additionally, it was able to identify molecules with high electrochemical capabilities, such as EPA and tartaric acid. And this further proves that they can be applied as binders in the future. I was able to conclude that chemical properties and machine learning can identify robust binders that can make silicon anodes a feasible source of high energy dense power in the future. Future research, I would like to test other nonlinear models such as Gaussian processing, or improve my sample size through a silicon battery database. Finally, I plan to go into a lab this summer to validate the accuracy of my model by actually testing EPA and tartaric acid as a binder in these silicon batteries. Thank you for listening to my presentation. Here are my references. Are there any questions?
Thank you, Ryan. Thank you for that presentation. Questions. So there is one from Pranay. Pranay, do you want to come off screen and ask your question?
So I had a question about how can battery manufacturers actually like apply this model to improve battery performance? And if so, then how much can they actually improve?
Well, it wouldn't necessarily be battery manufacturers, but more like battery chemists. But they would be able to use this machine learning model to, maybe they would be able to like contribute to it and improve the sample size. But what that would be able to do is they'd be able to basically test different binders without actually having the equipment, and they could just basically put what the parameters of the molecule into the model, and it would be able to output a predicted capacity retention. So they would be able to test batteries without actually testing them.
Okay, cool.
Great. Thank you for the great question, Pranay. Any more questions for Ryan? Ryan, I have a question for you. For what applications or environments would silicon batteries not be optimal?
I'm sorry, can you repeat the question?
So for what applications would silicon batteries not be optimal?
Well, currently, silicon batteries are not optimal for like for anything because of their degradation, but their very quick degradation. So right now, they basically have no application because nobody wants to have a battery that dies immediately.
I see.
But I guess silicon batteries are limited in that you have to like charge and recharge them. But there are probably things that don't need charging or recharging, like just pure like battery, like Duracell batteries. You probably don't need silicon in those because those don't care about like charging or recharging. So that's where it would be limited.
Got it. Great. Well, thank you, Ryan, for the excellent presentation and the strong results. And if people have more questions, feel free to ask them in the chat. And